All right, in this explainer, we're going to build a really intuitive feel for the physics behind MRI contrast. We're going to get into exactly why things like fat and water and all the other tissues look the way they do, why they have the T1 and T2 values that make our images so incredibly powerful.
So here's the game plan. We're starting with the absolute core mechanism, the dipole-dipole interaction. Then, we'll look at what controls it, and we'll use those rules to understand T1 and T2 in actual tissues. And finally, we'll see how it all comes together to create image contrast. All right, let's jump right in.
First things first, we have to talk about the engine of relaxation. Seriously, if you get this one concept, everything else is going to click into place. It's the key.
So what is it? At its heart, it's actually pretty simple. You know how every proton is like a tiny spinning magnet, a little dipole? Well, just like the magnets you played with as a kid, their magnetic fields interact with each other, right through space. They don't have to touch. And this magnetic chatter between protons is what lets them exchange energy and lose their alignment. And that, right there, is relaxation.
And this image here, it just shows you exactly what I'm talking about. You can practically feel the magnetic field lines from that proton on the left influencing its neighbor. This through-space conversation is happening constantly, all over the body, between billions and billions of protons.
So look, the main thing to remember here is that for the hydrogen protons that we actually image in MRI, this dipole-dipole interaction, it is the main event. It's really the fundamental reason we can tell the difference between all the tissues in the body.
Okay, so if this interaction is the engine, what are the rules of the game? What controls how fast that engine runs?
Well, there are four main things that control how strong this interaction is. And while they all matter, for understanding the contrast we see every day, we're going to focus on the two most critical ones: the distance between the spins and how they're moving relative to each other.
Now this is wild. The effect of distance is just huge. The strength of the interaction doesn't just get a little weaker as protons get farther apart. It plummets. It drops off with the sixth power of the distance, r. That means this is an extremely short-range force. Protons basically have to be elbow to elbow, usually in the same molecule, for this to really work.
And this visual, this really gets to the heart of T1 relaxation and the role of motion. See, T1 is all about exchanging energy. And that energy exchange is most efficient when molecules are tumbling at a very specific speed, the Larmor frequency. Think about pushing someone on a swing. You get the best result when you push in sync with the swing's natural rhythm. For protons, the Larmor frequency is that magic rhythm.
All right, so we've got our two key rules, right? Short distance is crucial. And for T1, there's this Larmor frequency sweet spot. Now, let's put them to work and explain why different tissues have the T1 values they do.
This graph right here is going to be our best friend for the next few minutes. On the vertical axis, you've got the T1 relaxation time. And on the horizontal axis, you've got how fast the molecules are tumbling, from slow on the left to super fast on the right. That lowest point on the curve, that's our sweet spot. It's the most efficient relaxation, which means it's the shortest T1 time.
So let's start with free water. Think CSF or the fluid in a cyst. These little H2O molecules are just zipping around, tumbling incredibly fast. They're way out on the far right side of our graph. Their tumbling is just too fast to have an efficient chat at the Larmor frequency. So relaxation is really inefficient, and that's why T1 is so long.
Okay, now let's go to the complete opposite extreme: solids, or maybe something like ice. Here, the protons are basically locked in place. They're tumbling very, very slowly, way off on the left side of our graph. And again, their speed is a terrible match for the Larmor frequency. The energy transfer is inefficient, and so T1 is long.
So, where is the sweet spot? Well, it turns out that fat molecules, because of how their long carbon chains rotate, happen to tumble at a rate that's remarkably close to the Larmor frequency in most scanners. The very same thing happens with water molecules that are kind of stuck to large proteins. This perfect match makes their T1 relaxation incredibly efficient, and that's why they have a short T1.
And check this out. This perfectly shows you what we mean by bound water. On the left, you can see those water molecules kind of clinging to that big macromolecule. This interaction slows them down. It literally shifts them from that too fast region on our curve over to the left and drops them right into that just right sweet spot for fast T1 relaxation.
Okay, so that's T1. Let's switch gears. We can use the exact same principles of molecular motion, but we're going to see they lead to a totally different result for T2 relaxation.
Whoa. Okay, look at this. The
The second you see this graph, you know something's different. That blue T1 curve has that classic U shape we've been talking about, but the red T2 curve, it just keeps going down. As molecules get slower and slower, T2 just gets shorter and shorter. There's no sweet spot. So, what's going on here?
All right, here's the absolute key difference you need to remember. T1 and T2 are both driven by that same dipole-dipole interaction, but they care about different effects of it. T1 is all about losing energy, which works best with motion at the Larmor frequency. T2, on the other hand, is about dephasing, protons falling out of sync with each other because of the steady local magnetic fields of their neighbors. And the more static or slow-moving those neighbors are, the faster the dephasing happens. And now it makes perfect sense why solids have such a short T2, right? The protons are packed in tight, and they're basically stationary. This creates these really strong, unchanging local magnetic fields that just wreck the phase coherence of their neighbors. The dephasing is super fast.
And fat? Well, it's somewhere in the middle. The molecules are bigger and slower than water, but they're not locked down like a solid. So they do cause some dephasing, but not as dramatically as solids do. And that's why fat has an intermediate T2 time.
And that brings us back to our friend, free water. The molecules are pretty far apart, and they're tumbling and moving around so fast that from the perspective of any one proton, the magnetic fields of its neighbors just average out to almost nothing. With hardly any of that steady spin-spin interaction, dephasing is incredibly slow, and that's why water has a very long T2. Okay, so we've dug into the why behind all these T1 and T2 values. Let's pull it all together now and see how this creates the beautiful contrast we see in our final images.
All right, let's do a quick recap for T1. Who's fastest to relax? Fat. It has the shortest T1 because it's right in that motional sweet spot. And who's the slowest? Free water. It's tumbling way too fast, so it's the very last to recover, giving it the longest T1.
And now for T2. It's almost the mirror image, isn't it? Solid tissues, with those strong, static local fields, dephase the fastest. They have the shortest T2. And free water, with its rapidly averaging fields, holds onto its phase the longest. It has the longest T2. At the end of the day, these deep physical differences are what we exploit to make an image. By choosing our timing parameters, our TR and TE, we can selectively highlight these differences. We use short timing parameters to create a T1-weighted image that makes things with short T1s like fat, bright. We use long parameters to create a T2-weighted image that makes things with long T2s like water, bright. The physics of how molecules tumble, filtered through our choices, becomes the amazing contrast we see. Which, of course, leaves you with one last thing to think about. If T1 is all about hitting that sweet spot at the Larmor frequency, what do you think happens to our T1 contrast when we change the main magnetic field strength?